Hi, today we're going to discuss sound waves. All sound comes from vibrations and travels in waves. Waves are formed by creating a disturbance in a solid, a liquid, or a gaseous medium, which transmits energy from one place to another. When particles are pushed together, they're called compressions, and when they bounce away from each other, they're called rarefactions.
When we think of waves, we often picture water. Ripples on a pond or ocean waves out at sea are called transverse waves.
Transverse means the wave direction is perpendicular to the medium. Transverse waves can be produced by throwing a rock into still water to cause ripples. Watch the ripple waves in this pan caused by the energy disturbance, in this case, a magnet. Transverse waves have troughs, the bottom of the wave, and crests, the top of the wave. Sound waves, however, are not transverse waves. They are called longitudinal waves. These waves move in the same direction as the medium, regardless if the medium is solid, liquid, or gas. Transverse and longitudinal waves can easily be demonstrated using a $4 slinky, which is also fun. If you hang on to both ends, you can make transverse waves right in front of you, the compressions and rarefactions moving through the springs. The sound travels in longitudinal waves, more like this.
Here you see the slinky and the longitudinal wave look almost identical.
Some energy is transmitted through both longitudinal and transverse motions. These are called surface waves. For instance, as an ocean wave approaches a shoreline, its speed starts to differ between the top and the bottom of the wave. The bottom of the wave slows down due to friction created as it moves up a beach. The energy is forced into almost a circular motion until the wave topples over. If you visited the seashore, you felt the power of those waves. A fun way to experiment with longitudinal sound waves is to use a tuning fork. Tuning forks have tines, just like the forks with which we eat. When you strike the tines, the disturbance vibrates the air, causing compressions and rarefactions. The compressions and rarefactions of disturbed air molecules form the sound wave, which travels to our eardrums. Remember the gentle ripples caused by dropping the magnet into the tray of water? Now watch as longitudinal waves, via this tuning fork, are dipped into the same tray of water. Did you see the splash up everywhere? The longitudinal effect on the water, the vibration, caused it to splash out because there's nowhere else for the water to go. There's no ripples, just the splash. The rate at which waves pass a particular point within a given amount of time is called frequency. The higher the frequency, the higher the sound is to our ears. You can see these are different sized tuning forks. Now listen as they have a different higher or lower tones based on their manufactured frequency.
People hear at different frequencies than many animals. Some animals, such as bats, communicate at frequencies outside of our range of hearing.
Waves not only can be measured by frequency, they also have a measurable height. The size of a wave, a sound wave, from its top crest to its bottom trough is called amplitude. In sound waves, the greater size the amplitude, the louder the sound is perceived by our ears. This can be demonstrated by placing a tuning fork on something to increase its amplitude, what every musician knows as amplifying a sound. The material, the size, and the shape of a structure often determines its ability to amplify sound. Listen for the different tones generated by these different types of tree stumps. Different shapes and different surfaces transmit the energy at different amplitudes. That's the American beech. The red maple is slightly quieter. The black locust hardly transmits it at all. The white pine, however, has a grain that helps throw the music to our ears. It enhances or amplifies those vibrations. The white pine and other pines are used in many different instrument tops. But what happens if somebody makes a tree into a sound box? The white pine is the face of the violin, and the back is maple, which reflects the sound waves. So the sound waves are amplified, given greater volume or more amplitude with the help of the pine, and then reflected through the holes off of the maple, which is a much denser wood.
Sound waves can also bypass a person's eardrum and travel through our bones directly to our inner ear, the cochlea. This is how whales and dolphins and other marine mammals can hear each other through water, and also how sonar works by sending a vibration through the water and timing its return to the boat.
Sound waves then stimulate our auditory nerves and are translated to sound by our brains. Ludwig van Beethoven famously discovered this on his own. As he slowly lost his hearing, he would still play the piano, grip a pencil in his teeth, and press it into the wooden soundboard. The sound vibrations would travel through his jawbone to his inner ear. The next time you notice the music of a bird, or someone's voice, or a musical instrument, try to imagine the actual waves traveling between the molecular air disturbance and you. Enjoy catching the wave.